example. Welcome to our YouTube channel. Today I will be explaining you all about the Sauty bridge. The Sauty bridge, it is the simplest method of measurement by comparing two capacitors. As you can see in the circuit diagram, we have capacitor 1, capacitors 2, then we have resistor and two resistors which are connected to a main AC power voltage. So this bridge is the simplest method of comparing two capacitors, and we can say that it is mainly used for measurement of capacitance of a capacitor by comparing it with a standard capacitor. As you can see, C1 will be our unknown capacitor and C2 will be our standard capacitor. We'll look more into it in our next slides. So this bridge, the construction of this bridge is very simple. We have two capacitors and we have two resistors, in between we have a detector. Then in A and C, as you can see, we have denoted each node here with A, B, C, D, where the A and C is connected to a AC power voltage supply, and this is the voltage in this AC power supply is denoted as V. In arm AB, the voltage is V1. In arm BC, the voltage is V3. In arm AD, the voltage is V2, and in arm DC, the voltage is V4. In arm AB and AD, we have a capacitor, so we can say that the impedance of this arm AB is equals to C1. So we can say that Z1 is equal to C1. Similarly, in arm AD, we have capacitor 2, so we can say that Z2 is equals to C2. We know that as I already said in my previous slide, that the C1 it is the unknown capacitor and C2 it is the standard capacitor. In arm BC and CD, in arm BC you can see that there is R3 as a resistor and R4 resistor. In arm CD, these are non-inductive resistors. We are using non-inductive resistors here because for accurate measurement. When we use other type of resistors here, it creates some type of error. So to avoid that, we are using non-inductive resistors. So coming into the balanced equation, the AC bridge balance equation, which is given as Z1 times Z4, which is equals to Z2 times Z3. So before coming to this video, you can check our playlist where my friend has explained to you all about the AC bridge balance condition. So we already know that the impedance, the capacitor in impedance form can be represented as 1 divided by j omega c, where for the inductor it is j omega l. So at balance what happens is Z1 times Z4, which is equals to Z2 times Z3. This is the balanced equation. So to get the value of the unknown capacitance, we substitute Z1, which is simply 1 divided by j omega C1, and R4 remains same because Z4 here is the resistor, and the resistor remains same. So 1 divided by j omega C1 times R4 is equals to Z2. Z2, we have capacitors 2, which is the standard capacitor, and it can be written as 1 divided by j omega C2 R3. Looking at the right hand side and the left hand side, we can see that j omega and j omega can be cancelled, and it can be arranged in the form C1 divided by C2, which is equals to R4 divided by R3. And by arranging, therefore we know C1 is equals to C2 times R4 divided by R3. So here C1 is the unknown capacitance and C2 is the standard capacitance. One important point we should mark in Sauty bridge is that the Sauty bridge, it measures the value of capacitance which are free from dielectric loss. We can also say that the capacitor should be an ideal capacitor. Otherwise, if the capacitance of the capacitor is not ideal, then this bridge will not work for the proper measurement of the capacitors. Therefore, we have to have an ideal capacitor for the capacitors which are free from dielectric loss. Otherwise, there is another bridge, another version of Sauty bridge, which is called as modified Sauty bridge, which is used when the capacitor is not ideal. So if we are to talk about the phasor diagram, before going to the phasor diagram of the Sauty bridge, we have to know that for the resistors, the voltage and the current, they are in the same phase, and for a capacitor, the voltage lags the current by 90 degrees. So if you look at the circuit, we can see that the current I1 and I3, right now it is denoted as I1 because in balance condition what happens is the voltage in the arm AB and the arm BC, they are equal. So we can say that I1 is equals to I, so that's why we have denoted this current, the current flowing from this, as I1. So that's why we can denote I1 which is equals to I3. Then since the I2 current flows from here and the I4 current flows from here, so we can also say that I2 is equals to I4. And in the balance condition, we can say that V1 it is equals to V2 and V3 it is equals to V4. So the phasor diagram here, we need to first keep a reference. So we will keep I1 as the reference line for this phasor diagram. So the I1, as you can see, the I1 flows from the capacitor C1. The capacitor C1, the voltage in the capacitor C1, so the voltage in the capacitor, we know that it lags the current by 90 degrees. So here, so the voltage of the capacitor can be written as I1 divided by j omega C1. So I have written it like this: it lags the current by 90 degrees. And since I1 also flows to the resistor R3, since in resistor the current and the voltage, they are in same phase, so here I2 is written in phase with the current I1. Similarly, current flowing the current I2 flowing from C2, we can, as we already know that V1 it is equals to V2 and V3 it is equals to V4. Therefore I1 divided by j omega C1, which is equals to I2 divided by j omega C2. Therefore we can say that this capacitor also lags the current by 90 degree, and the similar happens to the resistor here, they are in the same phase. So the resultant, as we can see that V1, V3, V2, V4, they are all equal to the main voltage, which is V. So V1 plus V3 gives us V, and also V2 plus V4 also gives us V. So the resultant vector from this two I1 and this, we get a resultant vector which is equals to V, and this V is equals to V1 plus V3, and it is also equals to V2 plus V4. This much is for the phasor diagram. Next we will be talking about the advantages and disadvantages of this bridge. So the advantages and the disadvantages are pretty simple. Pretty simple, no?